Unit 11, section 11.6, computer output. This is going to be our last section in our unit on exploring two variable data. We've just been looking at how well our data or our model fits the data. So we used residuals, which helps us create the least squares regression line, R squared, which is our correlation coefficient, which tells us how much our model represents the variation that we're seeing in the Y, the response. We talked about the residual plot, and S, our standard deviation of the residuals. And again, using that to kind of tell us, is our model a good model for the data? And so the last part today, we're going to look at computer outputs. And so statistical software such as Minitab or JMP will record many features of linear regression in their output, including the slope and y-intercept of the regression line, the coefficient of the determination, which is our R squared, the standard deviation of the residuals, S. It also includes some information that we'll learn later in the course here. So that is our T values and our P values. That comes back from, again, this is unit 3 in our book or in our units, and unit 11 at the end here. So here's the computer output that for the problem that we've been working on the Ford F-150 truck data. And so this is the Minitab, and then this is JMP. And you don't have to know what those are or the programs or how to use them, but what we do need to know is how to interpret them. So AP mainly will use our Minitab display, and I've seen the JMP outputs before, but rarely. Then on on College Now, we typically see our calculator screen output, so that's going to be more typical to what we've seen. So looking at Minitab, we have these ideas here where we have our predictor, our constant, and then the miles driven. So when we look at this piece, they're giving us our coefficients here. That's what COEF is. So when we're looking at that, they're telling us, okay, here's the coefficient for the constant. Here's the coefficient for the miles driven. That's our X coefficient. Remember, this is about the miles driven and then the price that we had. And so they're telling us, here's our X, and that's going to be our predictor for the money overall. X is the coefficient here for miles driven. Our coefficient for the constant, our B term, would be the y-intercept. Then it also gives us the standard deviation of residuals, which we talked about in 11.5, and it gives us R squared here. It calls it capital R squared, 66.4. We won't be using this, and we won't be using any of this output. It does give us P values and our T critical values, but we won't be using that as far as our interpretations here. In a similar way, JMP gives us our R squared and the root mean square error. And again, this one's a little bit more unusual to see, but it does give us the intercept and again, the miles driven there. The same information that they gave us there, but we don't need all this other information as well. Most of the time we're going to see this, so we're going to look at that as well. So here's our example. It says a random sample of 15 high school students were selected. The foot length in centimeters and the height in centimeters of each student were recorded, and the least squares regression was performed on the data. A scatter plot with regression line, a residual plot, and the computer output from the regression are shown below. They've given us a lot of information here. However, they did not give us the 15 measurements. So here's our scatter plot here. So this is our scatter plot because it's relating foot length to height. This is our residual plot relating foot length to how far off we are from our line. And then here's our here's our Minitab outputs with our coefficients and R squared and S values. So when we're looking at this, they're providing a lot of information and they're going to ask us to interpret things. So on the first part, it says, what's the equation of the regression line? Define your variables. So there's two ways that we can define our variables. We can say, okay, y hat, that's our predicted line, is going to be the constant 103.4100 plus our x coefficient, 2.7469 x. And we can say, okay, this is going to be where y hat is the predicted height, and x is your foot length. Okay, another way that we could have defined our variables, so here's part one. Here's a second way we could have defined it, is inside. We could have said, here's our height. That's our predicted height. It has the hat on it there. Using the same numbers, 103.4100 plus 2.7469. And then we could say, here's our foot length. Okay, that's going to bother me. Let me erase that and try again. So it's all written as one piece there. It looks like an afterthought instead of an equation. So we're going to try again. So on this one, if we had height equals the same numbers, and I'm going to fit it in here by rounding, times foot length. So now I'm defining my variables inside my equation, or I can define my variables outside of it. But this is where I'm getting my constant and my intercept. Or I'm sorry, good grief. This is where I'm getting my constant, the y-intercept, and my slope with the foot length x value. So on part B, again, this is just interpreting and knowing those things that they're asking here. So what does that slope represent? So we have a slope of 2.7469, and if I put that over 1, here's my rise over run. I can interpret that as for each additional 1 centimeter of foot length, okay, there's addressing my x value on the bottom. So for each additional 1 centimeter of foot length, there is a predicted height increase of 2.7469. Okay, so this is going to be our interpretation. I've addressed the 1 centimeter for additional foot length and how that's changing. It's increasing because it's positive. And so for each additional 1 centimeter foot length, there is a predicted height increase of 2.7469. Interpret the constant. Okay, so this would be 0 and the 103.41. So our constant here, we would interpret this as given a foot length of 0 centimeters. Okay, that's a little extrapolating here. This would be like if we cut off your foot, we predict a height of 103.41 centimeters. And again, this is all about our predicted height. Anytime we're talking about our values, when we're talking about the y values, there's a reason that we have this as our predicted constant, our predicted outcomes. Y hat, height hat. These are predicted, not observations. On D, it says find and interpret the coefficient of determination. So that's going to be our r squared value. So looking at the data they've provided, r squared is 48.6%. So we can pull that over here. And so interpreting that, we would say 48.6% of the variation in heights is explained by our model. the least squares regression line. This is an accepted abbreviation of that, and so you can use that in your explanations here. On E, find and interpret the correlation. Okay, so correlation is R. Notice that in our table, it gives us R squared, it gives us an adjusted, okay, well, we don't want that. It gives us T and P, standard error coefficients. It doesn't give us what R is, but it did give us what R squared is. So if I take the square root here of 0.486, I can find that that value is going to be 0.697. Okay, when we take a square root, we get a positive or a negative. This is positive because we have a positive slope here. If we had said we're decreasing in height, we would have a negative correlation. So in this case, at 0.7-ish here, we're going to say there is a moderate, and I would say positive association. Positive because our slope is positive because we can see that in our scatter plot here, positive. So there is a moderate positive association between foot length and height. Find and interpret the standard deviation of residuals. Okay, so that's our S value, 7.95 here. So S is equal to 7.95, and that's going to be the typical distance. So we're going to say this is the typical distance from the least squares regression line is about 7.95 centimeters. So when we're using our line to predict the height overall from foot length, our estimations are going to be typically within about 8 centimeters. That's what that's telling us. The smaller this is, the stronger our model. The stronger or closer to 1 or -1 is, the stronger our model. The closer to 100% this is, the stronger our model. So when we look at G, is a line appropriate model for these data? Okay, so there's a couple things that we can use. We have small, within 8 centimeters is pretty good there. Again, we're talking about 2 to 3 or 4 inches there. And then we have kind of not a ton of the explanation here, but again, it's not so weak that we would say we can abandon it. So when we look at is our appropriate, another thing we can look at is looking for the residuals. No pattern, relatively small values here. So all of this kind of goes into, is a line an appropriate model? I would say yes. Okay, there's no outliers. There's small, I'm going to say small-ish, an S value. We have a large-ish R squared, and no pattern in the residual plot. Okay, all of these I would say lend us to say our model is appropriate for this data. I don't think that we could say this is our guaranteed that we would be able to narrow down somebody's height from the prediction. That's where I'm saying it's small-ish. I would like to see this smaller to say it's a really appropriate model. It's appropriate, it's just not it's not a good, strong model. We would like this to be higher. We would like this to be higher. But there are no outliers. We have pretty within 7, 8 inches or 8 centimeters here is pretty good. R squared, we're saying we're accounting for almost 50% of the variation, and we have no pattern. If we could get those smaller, I think I would be more confident in saying it's a great model for using for this data. And our last example here, using summary statistics. So sometimes we're not given the computer output, a calculator output, or any of the data. But we can still use summary statistics to find the equation of our least squares regression line using the following. Our goal is to be able to write an equation y equals a plus bx. Here's two rules that it has to follow. Y bar, our averages, have to go through it. So anytime we have a scatter plot, okay, there's going to be some average here on X bar. There's going to be some average Y bar here that intersects there. And our line has, our line has to go through that. And so when we're looking at this piece, it's got to go through Y bar and X bar. So we're going to use this to our advantage. And our slope here can be found using the typical variation in Y over X times our correlation. So if we know the averages and the standard deviations with R, we can find the equation. So let's see how we can do this with summary statistics. So it says data from a random sample of 15, high school students investigated the relationship between foot length and height. So that same data. The mean and standard deviation of the foot lengths, so we have X bar 24.76 and standard deviation for X is 2.71, and the mean and standard deviation for Y bar 171.43 and standard deviation 10.69. Our goal is to be able to write the equation here. And the last piece it gives us is the correlation, R, is 0.697. We need all of this as a summary to find that information of the least squares regression line. So if I want to try to predict height from foot length, I'm looking to fill in a slope here and a y-intercept or constant here. And so I want to find these two pieces. This is where we have our A value and our B value and A plus BX. So I'm going to use the first thing that says, hey, let's find B. There's an equation for that. So B is going to be equal to R times the standard deviation of Y, change in Y, over change in X. So if I plug this in, we know R is negative 0.697. And the change in Y, we have 10.69. I don't know where I'm getting the negative. Whoop, that's R equals. I was like, hold on, we have a positive here. All right, I'm back at the ranch here. 0.697. I was like, we already said that had a positive association. So I'm plugging in a positive 0.697, a Y value of 10.69, out of my standard deviation of X, 2.71. Just like slope, Y's over X's, rise over run, and we can find that slope here to be 2.749. Now that's our slope. So we could plug this in and say, okay, here's our slope piece, 2.749. But now we need our constant. So we've used this piece to find our slope. There's step one. Step two, now we're going to use the averages here to find the constant. So I still don't know what A is, but now I have a slope, 2.749. I'm plugging in here times the average of X bar. So if we know those pieces, we can solve for A. We know the average here, 171.43, equals A plus our slope, which we found 2.749, times our average here for X's, 24.76. Okay, so we're going to solve that. I get 171.43 equals A plus, multiply that out. I get 68 0.07 here. I'm going to subtract that over 171.43 minus 68.07. And I end up with an A value that's 103.36. That's this value. So when I look at my least squares regression line, here's my equation. The predicted height, without a hat on, is equal to 103.36 plus 2.749 times our foot length. This is the overall equation for that. We had to use first our slope here, then our averages to find the constant. And so when we do this, it's not typical to have everything missing. Like we didn't give any of the measurements of 15. But if they don't give us all the measurements, they're going to give us a lot of information. They gave us the scatter plot, the residual plot, an output here, and on this one, all the summary statistics. If you need another example of this, let me know. We'll practice that. And then after that, we'll review and get ready for our test. Thanks. Have a good one.